for it is Owen Gwilliam, and he's going to be talking, he's going to tell us about generalized symmetries, factorization algebras, and nonabelian Poincare duality. Thanks, Chris.
Thank you to the organizers for the opportunity to speak. I know it's been a long day, so please slow me down or just ask me to repeat things, or I'll stop and do jumping jacks or something. Okay, so the goal today is to sort of lay out the target of the overall lecture series. So we're talking about symmetry, which is of course a long-running theme in mathematics and physics. You know, it was a driving force in the development of a lot of formalism in mathematics. For instance, the notion of a group and a group action developed exactly to capture some version of symmetry in geometry and algebra. For many of us, that's sort of the archetypal notion of symmetry. But since then, of course, there are things that have the flavor of symmetry that don't maybe fit exactly into that group action framework. So people have developed generalizations. It's sort of probably a familiar example. There's a notion of an infinitesimal symmetry or a Lie algebra acting on something. There are more general ones. So I'm going to survey symmetries in particularly quantum field theory. So the goal of the series is to survey sort of traditional notions of symmetry. UFT. So I'll talk about things like Notre occurrence and the Notre theorem, but also to explore more novel types of symmetry and how they're connected. So on the physics side, there's a notion called generalized global symmetries. Sort of keystone paper is from around 2014. There's been a lot of work in the theoretical physics community since then to reinterpret sort of known things, to explore the consequences of global symmetries, generalized global symmetries. So known things are things like center symmetries of gauge theories. You don't need to know what this is. This is the kind of thing we're going to get at. Got some really interesting consequences. There's a lot of activity. Sometimes people talk about categorical symmetries as well. So that's in physics. There's also a little bit before, there's a notion of factorization homology. And one of my goals is to sort of say how to interpret this kind of notion from physics using this kind of framework. So that means I need to tell you something about what all these things are. Not expecting you to know. Okay, great. So we're gonna have a survey, hopefully leading up to contemporary notions of symmetry. But today, we're gonna start in the most well-trod setting, which is symmetry. In that part of physics called mechanics. So there's maybe, I'm just gonna indicate loosely what I mean here. There's what we might call classical mechanics, to contrast with quantum mechanics. I'm going to assume you have some vague feel for this. So think about what Newton did. You know, writing down an ordinary differential equation, you know, force equals mass times acceleration. So this amounts to solving, let's see how I phrase it, solving ordinary differential equations, describing the dynamics of a system. So I'm gonna maybe write down some examples you met in high school really quick. So here's an example of a kind of system. You might think about a point particle moving around in ordinary space. So a point particle moving in free space. So we can think that's some trajectory in R3. But here's my loose visualization of R3, and the particle's having a really good time. It's running around, going on these little loopy curves. That's its trajectory through time. This trajectory is the solution to some equation. So something like the second time derivative, I view this as the time parameter, is some function maybe of the time, of the position, and of the velocity. Okay, so how it moves around is governed by some differential equation. So you notice that it depends on position and velocity, and then all the higher derivatives are controlled. So the solutions for most of the systems we study of this type are parametrized by position at some moment in time, velocity, or if you prefer, momentum. So the space of solutions looks like, we're thinking about position and velocity be the tangent space to R3. If you call it momentum, people often identify quotation. So this is supposed to be a kind of reminder of what we do in classical mechanics. So I'm running into the Constantine problem that my notes are bigger than the boards. Another example is you could think about a rigid body rotating in R3. So here's a rigid body. It's not symmetric, but let me fix one point. Then you can think about there being three little vectors painted in space that's sort of indicating what its orientation is, right? Those three vectors pick out a vector, a matrix, a 3x3 orthogonal matrix. So here you have a particle, or sorry, solutions are trajectories in SO3. Okay. Which means the solutions are parametrized by, say, the cotangent of SO3. And you can combine that by thinking about like this moving both in R3, maybe the center of gravity, as well as the rotations of this thing here. So we could also do a more general thing that combines moving in space and rotating. I'll talk about quantum mechanics a bit later in a way that's convenient for symmetry. So I'm going to postpone talking about quantum mechanics. So hopefully this is like vaguely familiar. Okay. So I tried to indicate what mechanics, sort of where it lives. I want to talk a little bit about symmetry in that setting. So this sort of broad framework, basic sort of formal model. In mind, there's at least two layers. We could think about a manifold. This manifold might be something like the space of solutions for our mechanical system, and a group G acting on it. Group acting. And here, I want to view that as a group homomorphism. This is a group map. The structure preserving maps of that manifold, so say diffeomorphisms. If G is a Lie group, we could also ask for the infinitesimal version. So if G is a Lie group with Lie algebra, here's my frac G. Okay. Then instead of mapping into diffeomorphisms, we map into the vector fields. Talk about a Lie algebra map. The vector fields on it, which has a Lie structure by the Lie bracket. So this is what we mean by an infinitesimal symmetry. So here a question?
No, we should probably just move the recording to the end.
Good point. Thank you. Everyone's tired. So I want to emphasize there's sort of a real, we call this an infinitesimal symmetry, but it has a really different flavor than what's happening up here. Up here, G is actually moving around the points of M. Over here, G is not doing sort of anything to M. What's it actually doing? It's really acting on functions on M. Okay, so if you want, interpret or understand this action, this infinitesimal action, via functions on M, right? So if I have, I don't know, X is an element of the Lie algebra, and it's acting on F, which is a function on M. This is defined to be, well, there's some vector field, let me give this thing a name, rho, the Lie derivative of rho on F, how that vector field acts, that function. Acting by a derivation. So just to anticipate a little bit, we're gonna interpret functions on M as observables on our physical system. So we want to sort of know how to think about and interpret that in condition. So this was just the general model. There was nothing in here about mechanics yet. When we saw manifolds, there's some extra structure available when you're doing mechanics. In mechanical systems, additional structure around. So the notion of symmetry gets refined. So I'm just going to assert what this structure is. Happy to answer questions about it like more later, maybe in that question period, about where it comes from. But the crucial structure is that C infinity of M in this case is a Poisson algebra. Does that mean not only does it have a way of multiplying things, a commutative product, it has a Lie bracket, typically denoted with braces. With the following compatibility, where for any function on M, the associated element here is actually a derivation or vector field. So another way of saying that is that this bracket is a bi-derivation, separately in each spot that satisfies the Leibniz. So I want to sort of track through what that ends up meaning in the level of symmetry. So over here, we already saw vector fields show up once. Now they've just shown up again. Let's put them in dialogue. So there is now a lifting problem. Like that kind of thing. So suppose I have G and it's mapping to vector fields on M, some kind of symmetry. Well, I also have this map from smooth functions on M, which people all call Ham for Hamiltonian. It sends a function to its Hamiltonian vector field, this vector field determined by bracketing with M. So we could ask, can I lift it? Does this infinitesimal symmetry factor through functions? If you have such a lift, it has a really interesting conceptual meaning. Such a lift is conceptually interesting. C infinity M codes the observables. The things you could measure about your mechanical system. So for instance, over here, in this example here, you might measure the position or the velocity or some function of that information. So here M would be something like this cotangent bundle in R3. There's a whole lot of things you could measure in principle about the physical system. Okay. So for any element over here, if I put it up here, so I'm saying that rho twiddle realizes symmetry, or the element of symmetry by X as an observable. This is the conceptually interesting part. There's no sort of obvious reason a priori maybe to expect that a symmetry has to be realized as an observable, but this is sort of a recurring theme in this subject, is to look for this kind of way of thinking about it. Something you can measure about the system. The symmetry is something you can measure about the system.
Sorry, quick question.
Yeah.
The Hamiltonian map should be like epic by just mapping coordinate functions down. Do we know anything about the kernel of that map?
Yeah, okay, so this is a very fun exercise. So suppose that M, I'm gonna do a special case. This is a fun piece to think about. This is symplectic. Okay. Then there's two sequences. You know what a symplectic form is? Do you know what a symplectic form is? This gives you an isomorphism between these. These are clearly just equal. And so I claim that the kernel of this is the kernel of this. And the image of this is contained in, is equal to the exact forms over here. In fact, being symplectic is the same thing as being closed. So there's like a fun little exercise to this. I don't know the answer for Poisson things. The answer is for Poisson things. I don't think there's like a general answer. Sorry, so
I have a question.
yeah.
So does this lifted at row like also lift to G to the lead group? Or
You shouldn't really expect it to, right?
should or not? Should
You
it?
should not expect that the group, I mean, like automorphisms in an algebra don't necessarily live in that, don't typically live in the algebra.
So even if the row action is coming from G,
Little g or big G?
big G,
Uh-huh.
then this lift shouldn't.
It won't, no.
No. Yeah.
That's a great question, though. Let's talk about our example. Go back to our two examples really quick. So if we're thinking about the particle moving in R3, right? So I could think about M being T star of R3 in the particle case. There's an action of translation. R3 is naturally a Lie group you can translate. That lifts to an action on the cotangent bundle in a very natural way. In this case, the Lie algebra is also R3 as an abelian integral. Very boring brackets. And the symmetry action of the Lie algebra, the infinitesimal symmetry does lift. And the symmetry lifts to a map from R3 to smooth functions on the cotangent bundle of R3. It sends infinitesimal, if I think about R3 being spanned by the d by dx1, d by dx2, and d by dx3. This goes to what people typically call the linear momentum. XJ direction. So these observables are the usual momenta you study as a high school student. Another example would be to this thing we did before of a rigid body rotating. Well, there's clearly an action of the group of rotations on this. This also lifts. Here G little SO3. And this map encodes the angular momentum as an observable. Okay. And the fact that little SO3 looks like R3 with the cross product is why you get all those weird formulas for angular momenta involving cross products. Okay. So one thing I really like about this is this problem of picking a lift ends up picking out observables that you know from experience are some of the most important operators or observables. This encodes angular momentum. They're some of the most important operators you study in a mechanics class, and they're manifestations of this symmetry. Of looking for the symmetry as observables. Okay. So, questions so far? Great. So, having a map like this from the Lie algebra to the observables, that's kind of the ideal manifestation of symmetry, infinitesimal symmetry, from my point of view. And we're going to look for other versions of it beyond mechanics. I want to develop now a slightly different way of viewing it. That's very suggestive and useful in the BB formalism as well. Okay, so at the moment, we're going to imagine we have a symmetry, and this is a Lie map, the algebra. I'd like to phrase things slightly differently, and the key is to use an adjunction. So there's an adjunction. Well, if I think about a Poisson algebra, it has both a commutative product and a Lie product, Lie bracket. So there's a forgetful functor where you forget the commuter product. What you're left with is a Lie algebra. Okay. Now, forgetful things usually have adjoints, left adjoints. So there's a left adjoint here. This points to the left adjoint. This is actually just given by the symmetric algebra. So let me explain that really quickly. So sim G is a Poisson algebra where we use the sort of obvious commutative product. We're just multiplying polynomials. It's a symmetric algebra. And we define Poisson bracket as follows. So notice that G could be thought about as the first symmetric power of itself. And that sits inside of the symmetric algebra. In fact, it generates this whole algebra under multiplication, right? So I have a map that goes from G cross G to G, which is the Lie bracket. But I could think about this copy of G as sitting inside of sim G. Okay. So I've told you how the Poisson bracket is supposed to act on generators. And a Poisson bracket has to satisfy this Leibniz identity in each slot. Okay. So I can extend it using the fact that it's the Poisson bracket is supposed to be a biderivation once I tell you what it does to generators. So values for behavior is extended. Okay, so SimG has this canonical Poisson bracket. Questions? Okay, so under this adjunction over here, we've got my beloved map. This is a morphism in this category. So I apply the adjunction. So this is, yeah, so under the adjunction, this determines a map from sim G to C infinity of M. So this was a Lie map. I'll call this rho again. This is a Poisson. I can write polynomials in elements of the Lie algebra and get observables as well, just by taking the product of those observables. So over here, I could take the linear momentum in the x1 direction times linear momentum in the x2 direction. That's a observable. So as a remark, this is some good terminology to know. Over here, and this map of Poisson algebras, so among other things, I have a map of commutative algebras, which you'd like to possibly interpret as coming from a map of spaces. So sim of G sits inside of smooth functions on G dual, where G dual is the the linear dual vector space. So G. Right, these are just happen to be the polynomial functions on G dual. So typically, there's a map of manifolds that goes from M to G dual as a manifold and called mu, such that rho is equal to pullback of functions. I take a function on here, I pull back on that to get a function on M. That's exactly what I'm seeing over here. A function on G and getting a function on M. This is called, this map of manifolds is called the moment map or the momentum map. That's because over here, it really is exactly the traditional notions of linear and angular momentum. This picture is really nice because you can imagine if I pick a point in here, I'm sort of fixing what momenta I see. I can think about the pre-image and restrict to thinking about the, this is a picture of G dual. And over here, I have M. And if I pick a point in here, I don't know, X, there's some pre-images. I can just think about sort of studying my system with those fixed values of the moment. Say conserved quantities. And foliate M by conserved quantities. Okay. It's going faster than I expected. It's a good thing or a bad thing. Other questions?
One more to go. G is equal to what? What is that notation there? G is equal to something superscript.
Oh, sim one.
Oh, sim one. Oh, okay.
The first symmetric power.
Okay,
Yeah.
gotcha.
So could you just show the moment of these examples?
I mean, I sort of told you what they were. You can certainly work them out. I'm not sure what kind of answer you would.
Yeah, I just like don't have much intuition for this. The last thing you said about the pre-image of a point.
So this one's very easy. Let's do the R1 case. Okay, let's do the R1 case. So if I think about T star R1, I can think about there being sort of the R direction and then the cotangent direction, right? So I can have like maybe an X coordinate here. This is like X comma, we call the coordinates in here X comma P, where this part is X, this part is P. So in this case, the moment map, I should have drawn this, makes a little more space, is projecting onto the P, it's the momentum. Okay. And that's just because if you're translating by R, the conserved, if you're translating in space, like you're always keeping it the same momentum. I can't draw this one. Oh my gosh, I want to actually. Okay.
What sense are they conserved quantities?
I haven't talked about dynamics, so I kind of hid that, but they're only conserved. I've only told you about kinematics. I didn't actually talk anywhere about picking what your ODE was. So I'm being a little bit sloppy there. If you asked for, to pick some force law that's governing how your system's evolving, if your force law is preserved by the action of the group, then you'll get conserved quantities. The trajectories will always preserve those functions. If it doesn't, then of course they won't be preserved. That's fair play. So turnabout is fair play. So one reason I like rewriting things as Poisson maps is it puts us in a good position to talk about quantization. So we're going to talk about a version of quantization that lets us sort of very naturally work with this notion of symmetry. So given a Poisson algebra over, let's say over the complex numbers. So that's 3 bits of data. There's a complex vector space, there's a commutative product, a Poisson bracket, which is a Lie bracket. A deformation quantization. An associative algebra no longer over the complex numbers, but over a formal power series in H bar. So Constantine's been carrying around this H bar as well at times. So I'm just doing power series in H bar. This underlying module, well, it has to be related to P. It's just formal power series of H bar over the coefficients of P. Okay. And the product, the associative product, for some reason, everybody writes it as a star. Satisfies 2 conditions. These 2 conditions are compatibility with the 2 different pieces of data. Okay. First condition is, well, I can think about all of these things modulo H bar. I just set H bar equal to 0 in times, right? And I just get left with a constant term. But if I have I take F times G, so 2 elements of P, that's just congruent to the commutative product on H bar. Okay, I guess since it's an H bar linear product, it's enough just to say what happens if I have 2 elements in P sitting inside of H. So in the purely classical sense, modulo H bar is ignored. You recover the commutative product. Now we're gonna have another condition that involves the Lie. Is that if I think about the commutator bracket using the star product, so this is F star G minus G star F. There's no reason for this a priori to be 0, right? I'm asking for it to be associative, so it doesn't have to be commutative. This is congruent to H bar times the Lie bracket, the Poisson bracket, mod H bar squared. Okay, so this condition told us that the commutator bracket at order H bar is 0, right? Because this is a commutative product. At the next stage, at H bar, I'm saying it's controlled by the. Okay. So there's a very nice kind of physics motivation for this. I told you the Poisson algebra is the structure that the observables have in a classical system. And we're saying, well, in the quantum world, the observables are just an associative algebra. That's some piece of insight we get from physicists. So we're asking to say, I can deform from my Poisson algebra to some quantum algebra in a controlled way. When H bar goes to 0, when I shrink it back down, I should recover the classical setup. And this tells me that the first order deformation is controlled by the Poisson bracket. I think a very attractive, at least, algebraist version.
The star product itself have anything to do with H bars? I don't know.
It's an H bar linear product.
Yeah, H bar linear, but does it also act by, for example, multiplying with H bar? Does the product itself depend on H bar basically?
Yeah, of course. It's got a H bar to the 0 term, H bar to the 1 term. Where these are like binary operations on P. They're like higher order differential operators typically. Absolutely, sorry. I don't know. Yeah, you can organize this product in terms of powers of H bar if you want. Because you can, right, you have a map. So you can think about picking subs here and then projecting out on these sides, breaking things up in all the pieces. Right. So let me give you an example, or in fact, the motivating example. The example is due to Heisenberg. He said, let's think about this point particle maybe moving in the real lines. Let's go back to our particle. And I'll write it on r random and r cubed just out of for simplicity. Well, there's two obvious observables we talked about. There's measuring the position of a particle at time 0. And there's measuring the momentum, we'll call P at time 0. And these satisfy this is what the Poisson bracket does between. Okay, so this is supposed to be the classical side. So Heisenberg just posited that in the quantum world, this corresponds to some new operator, which some element we'll call x hat in some algebra. Some operator p hat. So there should be corresponding operators, the quantum position, the quantum momentum, and their commutator, his normalization would be I h bar. You can see there's a very close relationship between there being an interesting Poisson bracket and there being an interesting commutator between these operators. In physics, people usually put an I h bar rather than this version I wrote here. So we could put an I there if we want. These are the sort of primary observables. Things are generated from them as an algebra. So as a remark, can, if you want, utilize x hat and p hat as differential operators acting with functions on R, and that might have been the way you've met it before. And this commutator is just a commutator between a first order differential operator and multiplication by x operator.
Sorry, could you help me understand like what the mod h bar and mod h bar squared are doing in this example?
I'm just straight up telling you there's no interesting h bar squared or higher direction. It's just like he said, there's only this first order in h bar thing involving x and p. Is that okay?
Does it actually define the deformation quantization?
He certainly Heisenberg didn't. I don't think Heisenberg knew what an algebra was, but he didn't know what a matrix was when he wrote this down. So
it's an example of a deformation quantization.
not if I take all smooth functions on R. We could do the polynomial functions. It's okay. Okay. Or are you fishing for something? Okay.
I don't remember if you could take all polynomial functions or.
I'm about to explain a slightly more general construction that will specialize to this one. So please ask me when I explain the enveloping. Okay. there's a theorem. And save it. So I'll paraphrase in the following way. Every Poisson manifold has a deformation coefficient. There is one over here. I'm being so there's it's like this Weyl formula thing.
Yeah, well, that's. I thought there's something that, I don't think you can really extend this to all some functions, not even all can.
Just speak up a little bit.
Sorry, maybe I want to be
Why don't I
quiet.
look that up? I don't know the answer to that. I don't think there's a problem, but I can look it up. Yeah. Weyl products.
Model product.
Great, yeah. Why don't we talk about that afterwards? Okay. So there are lots of examples of these kinds of things. This theorem, by the way, is a wonderful and very complicated thing to study. But let me give you a more algebraic example. Because we want to get to symmetries, right? Remember, we're going to deform this side, the smooth functions, we're going to deformation quantization here. So we need to figure out hopefully something parallel on this side. Another example. For GOE algebra. Poisson algebra we just met 2 minutes ago produced that adjunction. They're very nice. There's a functorial deformation. Write it in the following way. It's actually, you don't even have to go over power series in H-bar. I can just go over polynomials. Okay, so I'm going to take the tensor algebra on G. So that's the free associative algebra on G as a vector space. And then I take joint polynomials in H-bar. And I'm going to mod out by the following ideal. X tensor Y minus Y tensor X is set to be equal to H bar times the commutative bracket of X and Y. Okay. And this is for these generate an ideal where here X and Y denote elements of the Lie algebra G. So it's these live in the second tensor power. This lives X tensor Y, X bracket Y lives in the first tensor power of G, but it's not weighted by H bar. Okay. So notice that when we set H bar to 1, we recover a universal enveloping algebra. U of G, which is exactly getting rid of the H bar, setting H bar to 1. Okay. So let's call this thing, let's denote this thing. Just to remember that there's this extra H bar. I'm going to call this U H bar G is this. Okay, I want to point out that over here we can take the Heisenberg Lie algebra and do this process to get a deformation quantization. Okay.
Sorry, maybe this is an off topic, but if you,
It's an awful
there is also this quantum groups, right, which is the formation of the universal enveloping algebra. So it sounds like there are two quantizations.
Quantum groups are deformations as Hopf algebras, or even more as quasi-triangular Hopf algebras. I'm simply deforming here as an associative algebra, so they are deformation problems, but they're different types of deformation problems. And they have to do with sort of different physical situations. So this kind of deformation has to do with one-dimensional field theory with mechanics. Say the kind of quantum groups that Drinfeld and Jimbo study, these quasi-triangular things have to do with if you want three-dimensional field theories. But they have a similar flavor, so maybe with some inspiration. Okay. So I want to put together. We now have examples of deformation quantization for every Poisson manifold, and actually, in fact, for the kind of symmetry algebras we were thinking about. So I can now phrase, I think, a really nice problem. So we can phrase the question of quantizing a classical symmetry in mechanics the following way. So suppose I have a classical symmetry of my favorite kind. And this map. Rho. And now over here, suppose I pick some deformation quantization. This is a deformation quantization. Well, we've talked about there being a map from the quantum observables to the classical observables, which is just taking things mod h bar. So taking things mod h bar is a version of dequantization, going from the quantum to the classical. So on this side, Savage tells me I could, for instance, make something here. On this side, we have also our deformation quantization. So we could ask, can I produce a map of my deformation quantization of my symmetry algebra to my deformation quantization of my observables? This is, again, if you want, a lifting problem. There's a map from here to here, and I'm lifting it to here. So quantizing is picking a lift, or finding a lift. So remember, this is called, well, this is what the moment map does at the level of functions. So people call this kind of thing a map from this basically enveloping algebra, the algebra, to a deformation quantization. They call this kind of thing a quantum moment. This is one thing people call a quantum moment. A fair amount of geometric representation theory can be understood, if you like, from this point of view. So I want to wrap up, and any questions before I wrap up and sort of, yeah.
What's going from U H bar G down to symmetric?
It's down to here?
Yeah.
I mean, this is really boring. This is again mod H bar. So it doesn't know about the quantity.
Can we go both ways on this side of the diagram?
No. But what, I mean, there couldn't be an interesting algebra map from here to here, right? So, but by the way, and that's a really good, and sometimes it's a really good question, because physicists all the time talk about quantizing an observable or an operator. What they're doing is they are picking a lift, but there's not necessarily a canonical choice of lift. And this leads to a lot of ambiguities. They sometimes talk as if there is one, but it's not always one. Okay, go ahead.
So you have like some example of a quantum moment map.
I did look to see if I could find like a slick, quick one, but I don't have one.
Does it also have this like a junction formulation?
Does who have an attention?
The,
This side?
yeah. Like the first one, right, there is a like from M to the functions on the G dual. So does this also have some kind of formulation like that?
Right, on this side with the Lie algebras.
I just mean the quantum, so moment map usually goes from M to the functions on the dual, right? What about the
No, from
quantum?
N to the linear dual, linear functions on G. Right?
Sorry, yeah, so what about the quantum moment map?
Well, in as much as you can, question is, can you think about this as functions on a space? If you like to say words like that, you're doing non-commutative geometry. But non-commutative geometry typically is just taking op on the category
Right,
associated
right.
about this, yeah. So it's okay, I think it could be very kind of useful, but I don't have anything like deep to say there. It's like an affine associative scheme or something. Okay, sure. Okay, so this kind of framing of symmetry, so we, as say, having maps of Poisson algebras and trying to lift to deformations, I think of it as like a very nice model for how to deal with symmetries in general. So the basic goal of this, of next time, is to find a similar story. Not for mechanics, but for field theory in general. So this leads to a lot of questions. Like, what's a generalization? What's the appropriate generalization of observables for higher dimensional field theories? For instance, like, is it Poisson algebras or is it some cousin of Poisson algebras? What do we do to replace Poisson algebras in the classical setting? And what do we replace deformation quantization with in the quantum setting? Similarly, we have the question, what is a generalization of symmetries? Okay, so for a Lie algebra, what's the replacement of, say, the enveloping algebra or its Poisson enveloping algebra? There are people have thought about this kind of problem quite a bit. I'm gonna sort of offer an answer in the language of pre-factorization algebras in the remaining lectures. And the second, so tomorrow we're going to talk about the infinitesimal version. In the later talks, we're hoping to go back to things like groups acting as symmetries and what's the group version of this story. Okay, good. Thank you for listening. Please.
You mentioned that sometimes physicists will lift a moment map to a quantum moment map, but there's like a non-uniqueness in the choice of the lift. Is there like some sort of uniqueness up to constancy?
Well, sometimes you can't do it either. There can be an obstruction, and that's some like cocycle for the algebra cocycles. So sometimes you get, for instance, interesting central extensions that show up. But sorry, go ahead.
Oh, I guess that was it. You answered the question.
Yeah, so there's lots of, you can't always lift, and if you can lift, it's not so unique.
Okay.
But you can use the algebra cohomology to really nail down exactly what you have. It's a lifting problem. So of course, there's some kind of cohomology theory that controls it.
So it doesn't depend on the manifold or because
Of course, it depends on you're lifting the map, right? So it depends on everything.
Yeah. So what kind of homology is it?
Lie algebra with homology coefficients in the module of functions.
Oh.
Yeah.
Why this particular lift? So what tells us that this is a nice factorization work?
I didn't, over here?
Yeah.
So this is a functorial construction, so it's very attractive in that sense. And it recovers Heisenberg, so it's somehow the most familiar one, but if you can find another one that doesn't use this, I think it's probably interesting.
Are there some conserved properties, for example, if the lift fails using this one, does it also fail using other ones?
I have no idea.
This is part of conservation's theorem is that different deformation quantizations are isomorphic somehow by.
Yeah, I didn't want, but that's a kind of subtle way to articulate it.
Yes, I think also if you, I hope I'm not lying about this, but if you apply the consensus construction directly to the symmetric algebra of G, you do not get quite this algebra, you get that up to the floor isomorphism.
Ah, okay. He has a little discussion, right, about that, like one paragraph at the end of the paper. That's
Just.
I just want to continue my annoying comment. I remember
Great.
what I mentioned. So there's actually a no-go theorem for this.
That's
there's
lifting
no, there's no quantization
That's of operators.
functions of R that recovers this.
No, I think you're misreading like the Carnival and Hope, whatever.
So like the Moyard product doesn't have this effect. That's informed.
I'm just, in this case, asking for on the linear generators. It's okay on the linear part.
Yes.
And that's true here too.
Yeah.
It's true here too. It's just about two linear things, right?
My question was whether there's a deformation quantization of R that recovers what you wrote there. There is not.
There is, what there isn't is a splitting of this. There's not an algebra splitting of this map.
I don't think so.
Anyway, we should look at the statement of this theorem.
I think you have to relax the commutation.
I guess very naive question. It kind of seems like, so I understand physically why we want just like one H bar that we're varying everything with respect to. But like when we're defining deformation quantization, it seems like we could phrase things in terms of like a principal ideal and like having some sort of like field completion. And
I think it's absolutely interesting to study as a mathematician. There's tons of deformation problems that are really interesting. This is just a way of trying to capture the physicist's request in some sharp language. Okay. But I think as mathematicians, we study deformations of algebras over very interesting families all the time. I mean, so yeah, absolutely. No more sheets. I think they need some time to go set up there, and so don't go too far, but in 25 minutes or so, it should be ready to go.
Theorem is in this book.